morning, everyone. It's such a pleasure to be here to share my research with you. And I'm Zhou Shaobo from China Academy Railway Synthesis Corporation Limited. Today, my topic is rolling friction and wear testing of high-speed wheel rail materials with various hardness ratio. And my presentation will be given in these 4 parts. So, in the morning of this Monday, Professor Zhang and Dr. Zhou has given us a keynote speech about the development and some problems we might in China high-speed railway. Among these problems, the wheel rail degradation, for example, the wheel polygonization, rail corrugation, and some general common RCF defects like head checks and peeling are very common. Yes. And so all these defects has caused considerable maintenance cost for our maintenance work. And it's very essential to safety and comfort. And so we have come up with some countermeasure to deal with, for example, the wheel polygonization by shorten the lathing interval, or to do some reprofiling, or to adjust the components on the train. But we wonder if there is a way to deal with this problem from the material aspect. So we want to do something about the material selection and matching to prolong their service life and to minimize the cost. And as we know, in China we have several kinds of EMU tabs. So accordingly, we have cans of wheel and rail material using at the same time. So it's kind of complex for our study. And we distinct these different materials by the index of hardness. So we can separate them into different groups and do some twin disc rolling friction testing to find out if there is a optimal or the best group for wheel-rail match. So we collaborate with the Southwest Jiaotong University with Professor Wang. Yes, we do some rolling friction testing. Our test specimen was cut from the rail and wheel products, which is also used in reality. The specimen was cut as the sampling position shown here. And we have 5 cans of wheel material and 1 can rail material. Yes, these 5 cans of wheel material can be divided briefly into 3 hardness levels. And we can see that ER8, ER9, and SSW is very common for us because it's used in Europe and Japan. And the D2 is made in China, a Guanzhen steel group. So we have, generally say, we have 3 levels of hardness ratio of wheel and rail here. And the testing apparatus was, sorry, I didn't put a picture here, but the twin disc testing apparatus was shown in this finger. And the test parameter was shown here. We simulate the axle load set as 70 tons, which is the axle load of FH3 EMU type in China. And the spring rolling speed is 500 round per minute. The friction condition is very simple, it's dry. Because we have the same condition, we can compare different materials. And the super ratio is 0.75%. Vertical load, 1.5 kilonewtons. And in that, we got the Hertz contact stress of 900 millipascal. Sorry. So here are some results of the testing. First, I want to talk about the friction coefficient, because when you use different kinds of materials, it's very important to make sure that your friction conditions are the same. And all these 5 groups of testing specimens show the same tendency of the changing tendency of the friction coefficient. There shows a almost on the range, the same range of constant value of 0.3 to 0.4, and there is no significant difference between the 5 groups. So, under the same friction conditions, we can say the comparison of these materials' performance is reasonable. And on the right is the volume of our tested specimens. As you can see, the wheel's wear volume decreases as the wheel specimen's hardness grows. Yes, in the black, yes, the black one. And up in the finger, we can see a line and a blue line. This is the system Y of our specimen group. And we have the lowest system Y in the group of D2 and ERAC. And these are the surface picture of our test specimen. So we can see in the upper, the wheel specimen is filled with flake layer caused by contact fatigue and pits formed by cracking of the layer. And in the 5, we pick up 3 out of the 5 wheel materials, because we can briefly divide them into 3 hardness levels. So we make the order as the hardness level, and the right is the hardest, and the left is the softer. So as we can see that the surface can become smooth, more smooth as its hardness grows. And for the real specimen that counter the wheel, most real specimens share similar macroscope morphology, except for the real specimen coupled with the hardest wheel material, which is SSWQ3R. And in this way, we can see that as the hardness increases, the cracks, the surface cracks, tends to become smaller, as we found that the real material tends to wear more, and the surface roughness is kind of become larger. And then we sectioned our specimen to see the plastic deformation of these wheel and real specimen. So we can see that when the hardness of the wheel increases, the depth of deformation layer on the surface decrease. So it's very simple. It's very simple to understand that as the hardness increases, it's very hard to. It needs very high force to make it deformed. As this relates to one of the phenomena of the inequality, because we have wheel polygonization in EMUs, and if you set the wheel material harder, and then just to can elevate the polygonization, might have to elevate the polygonization of the wheel. So the crack length and the depths of these three kinds of wheel material decrease in turn. And this is, oh, sorry, this is the past. These are the crack lengths because after the test, we observed that the lamella has, we have cracks on the surface, observed cracks on the surface. And when the hardness increases, the cracks tend to be shorter and shallow. So, and besides, we collect the debris of the different wheels specimens as shown in the picture. See the down the page. We can see that the harder the wheel specimen is, the debris finally generates debris tends to be smaller. And this also explains why the hard wheels tend to have smaller cracks and minor Y volume. And this is very interesting because this also relates to the, might have explained why the hard wheels have the better resistance to the RCF. Because the cracks initiates at the shallower layer of the material, and it will get off, peel off the surface in the smaller pieces. So the cracks won't go deep into the material, and thus the RCF will not propagate. So, and there are some also discussion. So when the wheel becomes harder, resistance to wire and RCF tends to be better. But will it do harm to our real samples? Yes. And in this previous, we have some, can see that in this, when the wheel specimen is harder, we see our real well volume is growing, yes, and comes to the toppest when the wheel material is the hardest. So from this test, we see that harder wheel might have some impact on the real material and its well volume, and maybe degrades is faster. But as we observed from the field tests in China, that the well volume of the rail in high-speed railway is so small that the vertical volume on top of the surface of the rail is less than 0.1 millimeter for a year. So maybe there is plenty space for the improvement of the wheel's hardness. And does there exist a limit for wheel hardness? I may say it's right, yes. And because in traditional wheels, we thought that the harder wheels may have the smaller toughness index, and we may give rise to the risk of breaking. And how about real hardness? And as I have talked about, the wear volume of rail in high-speed railway is so small that there is a chance that we can set the real hardness lower to to cope with the degradation of the wheel. So it's a balance. Maybe we can make the rail to wear more and to protect the wheel. And here is conclusion. Yeah, when coupled with same rail specimen, harder wheel specimens are attributed to have better wear resistance. This is quite obvious. Okay, sorry.
Switch to the next presentation. I'm sorry, and the clock here is strange, so speaker cannot control the time.